All right, so now we'll look at some consequences of Cauchy's integral formula and Cauchy's general integral formula. In section 4.52, recall the extended Cauchy's formula, the general Cauchy's formula, stated that if f is analytic everywhere inside and on a simple closed contour C parameterized in the positive sense, and if C sub 0 is any point interior to C, then we can express an integral of a certain type in terms of the nth derivative of f evaluated at that point z sub 0. Nth derivative of f evaluated at z sub 0 is n factorial over 2 pi I integral about c f of z over z minus z sub 0 to the n plus 1, n being any non-negative integer. Okay, again, f is analytic on an inside contour C. Of course, the integrand here is not, because it's got the division by 0 at z sub 0. So we've seen examples where we can actually evaluate integrals of this form using function values, because all that requires is differentiation, and differentiation is straightforward. Integration, not so much. All right, so we claim this is a fundamental result in complex analysis. And here's some reasons why. It gives some behaviors of functions of a complex variable that just don't happen in the real setting. Next result is going to show us that if we have a function that's analytic at a given point, for us, that means that function is differentiable in some neighborhood of that point, then all orders of derivatives of that function exist. In fact, it's got a power series representation, as we'll comment somewhere down the road. But we're saying differentiable on an open neighborhood implies infinitely differentiable. Now, that doesn't happen in the real setting. Consider, for example, the function f of x equals piecewise defined x squared over 2 for x greater than or equal to 0, and negative x squared over 2 for x less than 0. That's differentiable. Its derivative is the absolute value function. But the second derivative doesn't exist. The second derivative doesn't exist at 0. Absolute value doesn't have a derivative at 0. So this kind of behavior of simply being differentiable doesn't imply infinitely differentiable, doesn't even imply twice differentiable in the real setting. We couldn't paste together functions like that in the complex setting to somehow create some piecewise defined analytic function. We've never touched piecewise functions in the analytic setting. Well, we may have had some contours and some contour integrals that were piecewise defined, but we never dealt with piecewise defined analytic functions. We can't. Here's why. So the theorem pertinent to this says, if a function f is analytic at a given point, then its derivatives of all orders are analytic at that point too. Well, that's going to be based on the extended Cauchy formula. Here, we're dealing with the nth order derivative and expressing it in terms of integrals. So with the integral existing, then we've got existence of these nth order derivatives. So let's look at a proof of that and a proof of a handful of other things. Okay. So statement is, differentiable at a point implies all orders of derivatives, or analytic at a point, or differentiable in a neighborhood of a point, implies all derivatives of all orders exist. Okay. So let f be analytic at z sub 0. All right, we're not going to really do an epsilon proof here. We just need a little wiggle room, as is common in analysis. Being analytic at a point z sub 0 means being differentiable in a neighborhood of z sub 0. So there exists an epsilon greater than 0 such that f is analytic in all points in a disk of radius epsilon and less than a disk of center z sub 0 and radius epsilon. All right, so all we did was say, hey, it's differentiable in this open region. We took an interior point and a little epsilon neighborhood about that point. All right, so let C sub 0 be a positively oriented circle. Mod z minus z sub 0 equals epsilon over 2. Okay, so we've done this cutting epsilon in half thing to guarantee now that this function, which we know to be analytic in this little disk of radius epsilon, then it's analytic on C sub 0, on this contour, which is centered at z sub 0 and has radius epsilon over 2. So we've got analytic on and interior to C sub 0. We need all that stuff so we can apply Cauchy's formula. F is analytic inside and on C sub 0. So for any natural number n, Cauchy's general Cauchy's formula tells us we get this relationship here. We've written this with s, integrals with respect to s, and the z sub 0 we've written as a z. We saw an example in the previous section with that kind of substitution. But we've written the nth derivative of f at z in terms of this integral. This being valid for all z in that, within that c sub 0 contour that we've introduced. Okay, so that tells us then that the nth derivative of f at z exists for all z in that little open neighborhood. So in particular, the n minus first derivative of f at z is itself differentiable because the nth order derivative exists. That being valid for any natural number n, we're good to go. So we can take derivatives of all orders of analytic functions with some details on what analytic means and where this can be done. Where you have an analytic function, take any one of those points where the function is analytic, you can take derivatives of all orders. And in fact, you can get power series representations out of these. Being infinitely differentiable is required for a power series representation. You see that in calculus 2 when you first encounter power series. It ain't sufficient though. There's a few more conditions than infinitely differentiable that are required for a function to be to have a power series representation, at least in the real setting. In the complex setting, it's a lot different story. It's if we've got analytic, we've got power series. That's why I tell you, you want to think analytic means power series representation. The next result, we've got a quote unquote proof here. This is a bit informal. Let's mostly gloss over this. It says if f of z can be written in real and imaginary parts, where this function f is analytic at a particular point, then those real and imaginary parts, the u's and v's, have continuous partial derivatives of all orders at the point. Yeah, well, a function has derivatives of all orders. We just saw that. And we can express derivatives in terms of partial derivatives. Certainly, we could get nth order partial derivatives with respect to x. You want nth order partial derivatives with respect to y. We could rewrite that, but we do have to appeal to Cauchy-Riemann. You want mixed partials. Same thing. We could get all of that with some involvement of the Cauchy-Riemann equations. But hey, if you got an analytic function, then the real and imaginary parts, partial derivatives of all orders exist and are continuous. All right, now for something a little bit new. Morera's theorem says, let f be continuous on a domain D if the integral about c of f of z dz equals 0 for every closed contour C in D, then F is analytic throughout D. Okay, we saw, well, here's where we saw it. We saw in theorem 4.44.a that if you had integrals like this always being 0, then the function had an antiderivative. In fact, that's the piece of theorem 44.a that we're going to use. Theorem 44.a was our fundamental theorem of calculus. We, at the time, thought of it as if f has an antiderivative, then we can use that to evaluate integrals, just like you do in calculus 1. It also had a third part it said something about integrals around closed contours being 0. So here's how the proof goes. We're going to take theorem 44.a and say, hey, f of z has an antiderivative, capital F of z. If integrals about closed contours are always 0 over a domain, then this function f has an antiderivative on that domain, which, by the way, you could use to evaluate integrals. That's our fundamental theorem of calculus style result. But here we're going for something else. We're going for analytic. Okay, well, here we've got this capital F of z. That's an antiderivative of f, or in other words, capital F prime of z equals lowercase f of z. And remember, we're taking this with the knowledge that analytic means infinitely differentiable, derivatives of all order. Okay, so f prime of z, capital F prime of z equals f of z, shows us that f itself is a differentiable function, that equality holding throughout domain D. So f itself is an analytic function. So that means f is differentiable, f is twice differentiable. Hey, and the second derivative of capital F is the first derivative of lowercase f. So this is kind of slick and brief. To show that f is analytic, we need to show that f is differentiable throughout domain D. Well, we'll associate it with the antiderivative, capital F. We know capital F is twice differentiable. We know capital F is infinitely differentiable, if you like, because we know that analytic functions are infinitely differentiable. That was the previous theorem that we had. So in particular, the second derivative of capital F exists, and so f is differentiable on domain D. That is, f is analytic on domain D. And one more result, and then we'll look back at the notes, deals with a bound on what will ultimately become coefficients in a power series, provided we get to a power series. Cauchy's inequality says, suppose that function f is analytic inside and on positively oriented circle C sub r centered at z sub 0 with radius r, blah, blah, blah. So the usual setting, analytic function, positively oriented contour, in this case it's a circle, and they've given us the radius of it, and centered at z sub 0. So nothing special there, the usual hypotheses. Here comes some more hypotheses. If capital M sub r is the maximum value of the modulus of f of z on that circle, then the modulus of the nth derivative of f evaluated at z sub 0 is bounded above, it's less than or equal to, n factorial times that m sub r divided by r to the n, this being valid for all natural numbers n. Okay, the fact that it deals with the nth derivative of f at z sub 0 certainly implies this has to have something to do with Cauchy's integral formula. And it does. By the extended Cauchy formula, the general Cauchy formula, we know that nth derivative at, say, point z sub 0 can be expressed in terms of an integral of this form. All right, now if we can get good bounds on this integral, then we've got a good bound on the nth derivative of f evaluated at z sub 0. So we want to bound on the modulus of this integral. All right. Well, we know that the function itself is bounded by m sub r. Don't know where that bound came from beyond hypotheses. That would be something we would have to find. So if we take moduli of both sides, we'll get an equality like this. The n factorial over 2 pi is real, so we can bring that outside the modulus stuff, positive and real. How big is f of z? M sub r. How big is z minus z sub 0? Well, z lies on this c sub r, actually, the c sub r curve, which is a circle of radius r and center z sub 0. So on a circle of radius r and center z sub 0, how far is z from z sub 0? A distance r. So we've got this want to say bounded by, we've got this z minus z sub 0 in modulus. We got that equal to r. So the denominator produces an r to the n plus 1. The numerator is bounded by, so we get an inequality, bounded by this m sub r that was given as the bound of the function. And back in section 43, I guess, we said if we can get a bound on the integrand and we know the length of the contour, that allows us to put bounds on moduli of integrals. So we've got this bound on the integrand, m sub r bounds the numerator, denominator equals in modulus r to the n plus 1. Contour c, or c sub r, had radius r. It was a circle of radius r, so its circumference or length is 2 pi r. So we get a 2 pi r here. The 2 pi here cancels with a 2 pi here. This r cancels with one of those r's in the denominator, leaving us with n factorial m sub r over r to the n, and that's what the claimed bound was. So, for what it's worth, there's a bound on the nth derivative of f evaluated at z sub 0. Back to the notes. That actually turns out to be a surprisingly useful thing. Morera's theorem, if we did more theoretical stuff, we might have some application for Morera's theorem. It's a converse of something we stated previously. Cauchy's inequality, in my humble opinion, plays a real central role in some interesting stuff. We're going to use Cauchy's inequality in the next section to give a proof of the fundamental theorem of algebra. Actually, we're going to give a proof of something called Louisville's theorem, which is an interesting result for functions of a complex variable. It's interesting because real functions of a real variable don't behave this way. But we'll use Cauchy's inequality to prove Louisville's theorem, and then we'll use Louisville's theorem to prove the fundamental theorem of algebra. And I'll go on at great length about how the fundamental theorem of algebra ain't really an algebraic result. It's really a complex analysis result. It's really a quick little easy corollary to Louisville's theorem, which is ultimately based on Cauchy's inequality, which is ultimately based on Cauchy's integral formula, if you want to track down the suspects in this line of reasoning. But with this background, we will have a very easy proof of the fundamental theorem of algebra. It's even the proof they use in the algebra class. In our introduction to modern algebra, when they prove the fundamental theorem of algebra, they don't prove it algebraically. They prove it using Louisville's theorem, Cauchy's inequality, and the Cauchy integral formula, it turns out. And that takes care of this section. So next episode, we'll look into the fundamental theorem of algebra and some other groovy stuff. I'll see you then.